Okay, so today, I have a couple goals. This will probably be a two-part talk. Today, at least, the goals will be to go over a small example. And in particular, I'm going to talk about D4. And then explain how and when we can analyze this. And then lastly, set up the Furbinius manifold formalism. So the Furbinius manifold formalism has to be set up because at least all the places I can see where you see this Steenbrink spectrum in singularity categories, they're all mediated by this Furbinius manifold. And so next week, maybe I'll talk a little bit about non-commutative Hodge structures and where we get the Steenbrink spectra in those. But in order to sort of talk about that in maybe a theoretically packaged way, I'll want to set up the Furbinius manifold. So I haven't said it yet, but the whole point of this talk is sort of to find where we see this spectra in singularity categories. Now, this spectra was described before in this seminar, but let me just give a quick rundown. So to a singularity, and this will be very informal, we can associate a spectrum of numbers. This spectrum encodes analytic information. Really what's happening is that there's some sort of mixed Hodge structure on the vanishing cycles of this singularity. And then the spectrum is giving you numerical information about the Hodge filtration. Right? You can sort of enhance this to spectral pairs and get information about the weight filtration as well. But the Hodge filtration is telling you a nice set of analytic invariants for the singularities. So I won't go over how these are defined, but basically, they're so the spectrum is logarithms of the eigenvalues of monodromy okay, and the integral part is given by the portion of the mixed Hodge structure, the qth portion. So this q is going to be your integral part that monodromy acts on. So for each eigenvalue, that eigenvalue is going to be acting on a certain piece of the mixed Hodge structure. And that qth part gives you sort of the integral value of the spectrum. Okay. So whenever we talk about these singularity categories, there's always a question of which one, right? There's like 5 different ways of defining these things. In particular, I'm going to be going over an example of D4 and sort of the ways I want to think about the singularity category for D4. I should probably put that in as a subscript. Is I'm going to be thinking about it as maybe the derived category of the directed Fukaya category of x squared minus y plus y cubed. And maybe also I'm going to think about it as the derived category of quiver representations over this quiver. You can also think about this as some sort of category of maximal Cohen-Macaulay modules, vector bundles, and also there's this definition in terms of a quotient of derived categories, but I won't need that at all. So thinking about this as a derived category of quiver representations, we get a sort of Euler form. The Euler form on dBq, well, if I have two representations, say I have a representation v and w, we get, say, the x zeros of vw minus the x ones of vw. But we can also think of this as the sum of vi wi minus the sum of vi wj. And I'll explain this in just a second. Where this vi and wi are dimension vectors of the representation. So in particular for D4, you just get a matrix that looks like, well, you get 1, 1, 1, 1. And you'll get, say, because the quiver looks like this, you'll get, say, a -1 here, just from this arrow, a -1 here, a -1 here, and then the rest are zeros.
So this comes from the exceptional collection on this category?
Yeah, that's essentially, yeah, it'll come from intersection information about the, so this is the directed Fukai category. So it's basically you take vanishing cycles, and then they intersect in a directed way. You only take a directed intersection of them, and this is sort of the intersection information of that.
So these vanishing cycle from exceptional collection?
Yeah, they will. Yes. So that's kind of a key point that I'll talk about later, is that they're exceptional collection. Yeah. For general singularities, yeah, but for ADE, for sure, for ADE, but general singularities, I don't think so. Maybe. Okay, and it's sort of a general fact from representation theory that if we take this, x inverse times the transpose, we get the Serre functor restricted to k naught. The Serre functor over on the other side corresponds to monodromy. And so what we actually have here is we have x inverse times x tau is the monodromy. So up to maybe some -1 or +1, this can be considered as, so chi can also be considered as the Stokes matrix. Of x squared y plus y cubed as an LG model. And maybe at the end of the talk today, I'll explain what I mean by that, just define Stokes matrix. But you can take this as just given for now. So in our example, we have S is going to be something along the lines of 0, -1, -1, -1, -1, -1, -1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1. So this is the monodromy of the D4 fiber, or the D4 singularity. So at least just from categorical information, right, just looking at a basis of representations, I should say the basis for this is probably just the simple representations. Just from looking at this information, we already have at least exponentials of the spectrum. So of course, that's not really the important information, but we at least have the exponentials of the spectrum. So how could we get the actual spectrum? Well, there's an idea that goes back to this physics paper by Sakori and Vafa. This paper is this on the classification of n equals 2 supersymmetric string theories, or supersymmetric theories. And the idea goes kind of like this. Well, they break it down. They say, OK, we'll take S and just write it as maybe 1 minus A, right? And they say, OK, well, let's actually find a parameter. Let's parameterize S. Let's do S of t equals 1 minus A of t, such that S of 1 is equal to S, right? And S of naught is equal to 1 minus A naught, which is just equal to 1. Finally, I need one more condition that we'll put on this, which is the condition that this is supposed to be chi, my bad. I'm not looking at the monodromy matrix here. I'm looking at the chi matrix here, this Euler form. And the condition I want is just this condition that x negative x negative x tau. This has, I should put eigenvalues in the circle. So the idea is that you're supposed to pick this sort of deformation of this matrix naturally from the identity to my chi matrix. Now what that means naturally is sort of up in the air. So in particular, I'll just put it like this and maybe talk about it in a minute. So choose this naturally. And we can sort of read off the integral values of the spectrum by doing this, right? What we're going to do is watch the eigenvalues as they rotate around 0. So we have all the eigenvalues sort of are 1 in the beginning, but then the eigenvalues start to rotate around the circle. And so the idea is that the integral value of of the spectrum is just the rotation number around this. Now, I should say this is up to some shift. This is up to a shift. In general, this is going to define something called the spectrum of the matrix. This is something you can define for any upper triangular matrix with ones on the diagonals. But then sort of something that they want to show, or they claim to show, is that up to a shift, this gives the Steenbrink spectra. Or maybe I should say not up to a shift, but after a shift. And so that shift, if we're looking at a function that looks like this, right, with m plus 1 variables, the shift is going to be minus m minus 1 over 2. That's what the shift number is going to be. So I should say the actual formulation is going to be the spectrum of this matrix is equal to the spectrum of the function minus m minus 1 over 2. So basically, this spectrum, the matrix of the spectrum, is always going to be centered around 0. So remember that these spectral numbers of f, these are centered around, say, n plus 1 over 2. If you're thinking about the Steenbrink spectrum, if you look at Sito's formulation, it's slightly different. And so this spectrum of S is always centered around 0, so just shift it over to being centered around 0, and you're good. OK, so there are several problems with this idea, though, or at least several assumptions that we're making that maybe aren't terribly founded. So in general, this is not rigorous. I forgot how to spell this word. Right. So basically, one claim is that we're always trying to look at matrices in this set, which is the matrices such that S is upper triangular with ones on the diagonal, and that have monodromy. Associated monodromy has eigenvalues in the circle. Right. So one claim that we would need is, is this connected? Can we actually make paths like this? Right? Can I come up with a path? Right. So 2, even if I do come up with a path, is this construction path independent? So basically, they say choose this naturally, but what does naturally mean, right? If I choose several other paths that are chosen naturally, quote unquote, is it going to matter? Am I going to get a different spectrum? So basically, what they say to do is they say to choose a path such that the eigenvalues, after they leave 1, right, they never collide together again. They never collapse. Right. So can I choose a path such that the eigenvalues don't collapse? And I suppose, can you choose a path like this naturally? In some sense, the simplest one. Right. So this is sort of a hard problem. I think this paper came out in the early 90s. And last year, there was some progress on this. Of course, I mean, to them, this was just a done deal. But as far as rigor formulation, we have this paper by Balnajan and Hertling. Which is in 2020, which basically says this. This works for two subspaces of TNR. We have THOR1 and THOR2. Okay. And what do I mean by this works? Well, there's actually two parts to whether or not this works, right? I've actually forgotten to mention one last thing, which is shift. These three allow us to sort of define the spectrum of this upper triangular matrix. But there's still this question of, does the shift give us the spectrum of F? Right. So when I say this works, I mean to define the spectrum of this matrix S. And I know I'm continually switching from chi to S, but we'll just say it's S from now on. That was my mistake writing these notes. And this gives the right answer for at least dimensions 2 or 3 or chain type singularities, which for our example will be enough because D4 after some change of variables and maybe some R equivalents can be written as a chain type singularity. And where a chain type singularity is just something that looks like this. That's basically what a chain type singularity works like. When I say dimensions 2 and 3, this is the dimension of vanishing cycles. So the Milnor number. So if I have 2 or 3 vanishing cycles, this will work. Or if I have something that can be written right after a change of variables, some sort of R equivalence as a chain type singularity, then this will work as well. So what are these subspaces? I'll just go over them really quick. So in dimension 1, this I think still works. I think it's rather trivial in dimension 1, but I have to check. Yeah, I think dimension 1's not a problem. So in dimension 1, the S is just going to be the scalar 1. Yeah. So there's not much you can do with that. The matrix will be just the scalar 1, and then the monodromy will just be the scalar 1. And the eigenvalues of the monodromy will just be 1, and then, you know. Right, but for, you know, if you only have, so for mu, this is saying mu equal 1, right? So in the ADE case, at least, so what is this? This is just A1, right? So it's just the sort of this singularity, right? And the spectral number is just going to be either negative 1/2 or 1/2, depending on your formulation. And this, yeah, I think, you know, I didn't work through this, right? But I think it works fine, right? There's only one matrix you have to worry about. That should be an easy exercise. Okay, so to do this, to define these subspaces, I'll define these sort of collections So basically all that's happening with this is we're taking a collection of n numbers. Remember, n here is the, for now, n is just the dimension of the space of vanishing cycles. And all this is saying is that we have, you know, they're symmetric about 1/2. These are not going to be the spectrum of the matrix. They're not going to be the spectrum of the function, but they're going to be related. They're going to be some sort of transformation of these spectra. All right, so we have these, and they're symmetric about this value, right? The second subspace is coming from this thing. And it's basically the same idea, but we're allowed to have some sort of number that's below this maybe pseudo spectrum. So in this, we're still symmetric about 1/2. We still have this symmetry. For all these numbers, except for maybe there's just this random beta 1 that's out here. So from these numbers, I can just form a polynomial. So to some sort of beta 1 through beta n, I can form a polynomial p, which is just going to be the product of x minus e to the negative 2 pi I beta j. Some sort of polynomial with these exponentiated eigenvalues. So this p is going to be equal to x to the n plus p n minus 1, x to the n minus 1 plus p naught. And the idea is that for HOR k, these are the matrices that look like this. We've got P1, P2, P2, Pn minus 1, Pn minus 1, Pn minus 1. Right, they look like this. So they have constant off diagonals, right? So you might be saying that our example doesn't work, right? Yeah. This is the scalars. Yeah, this is just, these scalars are just collections of numbers in this from 0 to 1 that look like this. They're symmetric around. This defines each subspace, right? So for T Hor 1 scalar, you can, anything in here, you can define a polynomial by doing this. You take this collection of numbers and you define a polynomial like this. And then the coefficients of this polynomial define a matrix. All the matrices that can be defined that way, that's what makes up this T Hor K matrices. Yeah, yeah. Well, K is just equal to 1 or 2. I didn't want to write both down. There's these make two different subspaces with trivial intersection. So, you know, the idea is that for either of these subspaces, if you find something that's in these subspaces, then the program works, right? Just sort of watching the eigenvalues run around 0 is like a well-defined process, at least. And that'll give you a spectrum of this upper triangular matrix. Right? So for these, you get a well-defined spectrum of the matrix. And so, at least, they also show that, you know, I guess I wrote this before, but they also show that if your f, if you take a function, some sort of function that's either a chain singularity, or you only consider vanishing cycle spaces with dimension 1, 2, or 3, then you should get, after a shift, you should get the spectrum of S. And the proof of that is basically to just compute the spectrum of these chain singularities and see what, and then compute also this the spectrum of these matrices that you're getting from the chain singularities, and then just show they match up. Right? It's nothing. So let's look at our example. So we've got D4. And say I just took what I consider to be a very natural parameterization. This is my chi of t, I suppose. Maybe I'll start marking this as in. So this m of t is going to be equal to negative t squared plus 1, negative t cubed plus t, t squared. We've got negative t squared plus 1, t, 1, 0, 0, 1, negative t, 0, 0. And the characteristic polynomial is just going to be lambda to the 4th plus 3t squared minus 4, lambda cubed plus negative 6t squared plus 6, lambda squared plus 3t squared minus 4 lambda plus 1. And if you watch the roots of this thing, you'll see indeed they are on the circle, and they sort of act like this at t equals 0, right? We just have all of them are just at 1, t equals maybe 1/4. one stays at 1, but the other two split off this direction and this direction. And then, you can keep watching this, but at t equals 1, you're finally going to get that this has moved all the way over to here. This has moved all the way over to here. And so we get the third roots of unity. But for the D4 singularity, so the Steenbrink spectrum of D4, this is just negative 1/3, 0, 1/3. And this spectrum of chi is the same thing. 1/3, 0, negative 1/3. And there's no shift in this case because the shift is just 0 for two variables. So you can run this program for all the ADE singularities, because they can all be made into chain type singularities. At least the simple singularities work. Now there's this argument that really all we should need to consider is the chain type singularities, but I don't think that that's, maybe I didn't understand it correctly, but I don't think that this is just the case that we don't have to worry about the shift actually matching up. I think this is still conjectural whether in general for even isolated singularities, whether after a shift, this spectrum of the matrix is going to match up to the spectrum of D4. But this at least shows us that in some cases, at least for these chain singularities, we can in fact get the Steenbrink spectrum out of the singularity category. Right? It's somehow encoded there. And what it's encoded by is actually the Stokes matrix. Right? The Stokes matrix for this singularity shows up in the category as just the Euler form of this quiver. Now, in general, what's happening is that this is an example of de Brovin's conjecture, right? Because, as somebody mentioned earlier, these vanishing cycles actually give an exceptional collection of this singularity category. And so, when we take the Euler form and look at a matrix of it, we're actually just looking at the matrix of this Euler form with respect to this exceptional collection. And at least the second part of de Brovin's conjecture is that this Euler form is going to match up with the Stokes matrix defining the Furbinius manifold, right? So this is how we got this. What's happening is that secretly, this is just an example of de Brovin's conjecture working. So I should say, maybe I should make a small note here, which is that this HOR matrix make a note. Maybe I'll use a different marker. So what this HOR means, so HOR for Perushalin, Orlick, and Randall. And these guys, these proved a fundamental result that basically allows the program that I just described to run. The result is something along the lines of proving a factorization of the monodromy matrix as a power, right? And not only just a power of a matrix, but a power of a very simple matrix. In that very simple matrix, you'll see, if you look at the paper, you'll see the polynomial I wrote up on the board appears as sort of coefficients of that matrix. At least the coefficients of the polynomial do. OK. So from here, I'd like to sort of transition into more of a mindset about Frobenius manifolds. Because everything we do from here on out is going to be mediated by these Frobenius manifolds. So let's go ahead and do Frobenius manifolds of a singularity. Right, this is classical stuff, but it still takes a lot of work to develop. So I'm going to go through it rather quickly. So say we just have this isolated singularity, right, F isolated. And say I define my Jacobian algebra. So to look at the Frobenius manifold, we're actually going to want to think about deformations of this singularity, versal deformations. So I'm going to construct the semi-universal deformation of this singularity. Which is going to be this capital F. So it's going to be a deformation of the singular fiber. Or not a deformation of the singular fiber, the zero fiber of this deformation is just going to be our original F. And notice that the deformation space is, the dimension of it is the dimension of vanishing cycles. In particular, to each generator of the Jacobian algebra, I can associate a vanishing cycle. So let's look at generators of the Jacobian algebra. Of QF. Right. Where this is a multi-index, not just a single index, or not just a single power. And so this semi-universal deformation is going to look like this, where we just multiply these generators of the algebra by some new variables ti. These ti are the variables of my deformation space. Right, the coordinates of Cu. So just like usual in singularity theory, I'm not just going to leave it like this. I'm going to restrict myself to some disks, or if you like, balls. And so this is going to be a disk of radius delta, a disk of radius theta. This is not just a disk. This is a mu-dimensional ball, I suppose. And I'm going to sort of make a Milnor fibration out of this big F, this semi-universal deformation. Right. So M is our Frobenius manifold. Now, I should say M isn't the Frobenius manifold because a Frobenius manifold is a manifold with a lot of extra structure, right? So M is the base space of our Frobenius manifold. But we need to have some sort of structure on the tangent bundle of this base space in order to get a Frobenius structure, right? So there's a lot of moving parts to these Frobenius manifolds. But let's see if I can sort of go over them in a timely fashion. So I'm going to look at the critical set. And I'm going to look at the projection critical set to the base space of the Frobenius manifold. Okay. What this allows me to do is I can identify the holomorphic tangent bundle. I can identify that with this push forward of the projection. Okay. What's going on here is if I take my tangents in the TI directions, this I can just map to the generators of my Jacobian algebra. Now, you might also see this written as this is the derivatives of my semi-universal unfolding with respect to these variables. Right? And if you look locally, what happens is locally at some value of this tangent bundle, you're just going to get a direct sum of these Jacobian algebras. Right. Right. So locally, it just looks like a direct sum of these Jacobian algebras. So where does the structure of this Frobenius manifold come from? Well, for Frobenius manifolds, you need a couple different things, and there's a lot of different ways to formulate them. But the first couple things you need is you need some sort of product structure on the tangent bundle, right? Beyond the product structure, you need an identity for that product structure, and you need an Euler form for that product structure. And then finally, you need some sort of metric that's compatible with the product structure. So where do these come from? We'll say this is going to be our Frobenius structure. The product is going to come from this thing right here. Because these are just functions, and I can multiply functions together. So that gives me a product for my tangent bundle. My identity also is just going to come from here. I can just take the function 1. After I take the function 1, this is going to be an identity for my product. My Euler element is going to be just this capital F. That's going to be a function in here. Sorry, this is consistent. This is the Euler element. So this is going to be 1. This is going to be product of functions. And this Euler element is just going to be F. And so the last thing I need to sort of define this Frobenius structure is a compatible metric. Now, of course, there's all these flatness conditions on all of these things. There's a laundry list of conditions. But before I can go over the laundry list of conditions, I need a metric in the first place to even think about them. So where could I get a metric? Well, I can basically push this forward. I get a isomorphism to this. These is going to be the relative differentials. So this is the, at least it's the push forward with respect to m of the relative differentials, the top forms of chi over delta cross m. Now, F was taking chi to delta, but here I'm thinking of this relative forms. The relative forms over this map, chi to delta across m, right? When I look at this, I'm taking xt. This is being mapped to f of xt, and then the second coordinate is just the identity. Right? So I'm taking relative forms over this, the top relative forms, and I'm projecting them onto m. right? Now, how do I get this isomorphism? This is basically choose a volume form. Because remember, this thing can already be identified with the push forward of functions on the critical locus, right? So if I choose a volume form for those functions on the critical locus, at least the push forward of them, that's where I get this sort of this map. And so sort of classically, this has a Grothendieck residue pairing. All right. And this Grothendieck residue pairing gives us this, this metric. Now there's a problem here. The problem is basically that I have a laundry list of flatness conditions for my Frobenius manifold. And if I just randomly choose a volume form, this Grothendieck residue pairing is not going to be flat. So So basically, these are the conditions that say all of these different tensors play nice with each other. We need this metric to be flat. We need this to be 0. The Lie connection. We need the Lie derivative with respect to the Euler element of the product to be equal to, multiplication on the left by 1, or on the right, I suppose it doesn't matter. And we also need Lie derivative with respect to this Euler element of G to be equal to d times G, where d is some complex element. This d will be important next week. And I need a couple other things. The derivative of G, when I just consider it with the identity in one portion, this has to be 0. And the Lie derivative of a product of two vectors, well, the Lie derivative of the product with respect to the direction being a product of two vectors is the product of one of the vectors with the Lie derivative of y, of the product plus y, product with the Lie derivative of x of the product. So there's this big long list of things. And it turns out all of these work. The only thing that doesn't really work, maybe, is this one. The flatness of this really depends on which volume form we choose. And I need to be guaranteed a volume form that makes this flat. And so this is a whole ordeal. Essentially, what we need to do is define these primitive forms of Cyto. So let's go ahead and do that. So let's go ahead and write down some stuff. So for this D, this is going to be phi of C. So the critical locus inside of delta cross M, right? I'm going to write phi prime as phi restricted to x, cut out the critical locus. I suppose this should be curly x. And if I take this is the sort of cohomology bundle around the central fiber, right? So this is the cohomological Milnor fibration of the semi-universal unfolding. Right? course, if I do the curly portion of that, I just mean this tensor global sections. And so what I'm going to do, the general idea is I'm going to look at a lattice in here. So I'm going to look at a lattice in here, and by a lattice I mean there's a topological Gauss-Menin connection on this, coming from the fact that this is a flat bundle, or sorry, it's a local system. So this is going to have a topological Gauss-Menin connection. And I'd like to sort of extend that topological Gauss-Menin connection over the critical locus. So we want to try to extend the topological Gauss-Menin connection over this thing. So in the classical case, if we just think about a singularity, right, not a semi-universal unfolding of it, but the answer to this question, what's the proper way of extending this thing, is the Brieskorn lattice, right? Because what the Brieskorn lattice does is it's the maximal sort of extension of the topological Gauss-Menin connection over the zero fiber that encodes all of the analytic information we want, but it isn't too big, right? The Brieskorn lattice is like the perfect lattice. And so what I'm going to do is I'm just going to define the Brieskorn lattice for this semi-universal unfolding. This is just the Brieskorn lattice definition, just over this semi-universal unfolding. And in fact, at the zero fiber, this is the classical Brieskorn lattice, right? At least if you take germs at zero, it's the classical Brieskorn lattice. All right. The next thing I want to do is extend this over P1. So what I mean by that is that this delta, I want to extend over P1. I want to extend this whole system over P1. So to do that, this is just solving the Birkhoff problem. So this is sort of a classical problem. We're solving the Birkhoff problem. So what I need to do that is I would find a monodromy invariant filtration. This is the general program whenever I want to solve the Birkhoff problem, is I can find a monodromy invariant filtration, say U, on this H infinity. And this H infinity is the flat multi-valued sections on this. Okay. It looks like I'm just about out of time. So maybe I'll say something quick about the rest of the program where you'd go from here, is that after you find this monodromy invariant filtration on the flat multi-valued sections, you get this extension. Okay. And once you have this extension, you can think of the residual endomorphism at infinity. And it turns out the residual endomorphism at infinity coming from the extended connection has eigenvalues that are negatives of the Steenbrink spectrum. Now, if you take the lowest Steenbrink spectrum number and take the eigenvector of that residual endomorphism, then that's going to, you can find a corresponding element in here, or sorry, a corresponding element in here that corresponds to that, and this will be your volume form. Sorry, I had it right the first time. So taking the lowest eigenvalue gives you an eigenvector. That's going to give you a volume form in here that gives us a flat metric. Okay, and maybe I'll pick this up next week.
Okay, thank you very much. Is there any questions?
Yeah.
So the new defined family X and Y is we are adding the new parameters for each of the
Yeah.
vanishing sizes. Just to get to the local geometric figure of the blow up of the singularity and the resolution of the singularity.
Oh. So you can define this spectrum by just blowing up and looking at the blow up. But I'd have to say I don't know. I would expect that yes. I expect that there is a connection there, but I haven't really thought of it, and so I would expect so, but I'm not sure. Yeah.
May I ask one question?
Yeah.
So, in the first part, you discussed about Steenbrink spectra from the singularity category.
Uh-huh.
So, you consider this category. So, you consider this, how can I say? Yeah, the symplectic geometry of the singularity.
Yes, so you can put like a symplectic form on it, and you can make it into a symplectic story, but yeah, for this simple of a singularity, you sort of don't have to talk about the symplectic geometry, but yes.
Oh, I see. Well, I mean, in the first part, you talk about the symplectic part.
Yeah.
In the second part, you talk about this complex geometry.
Uh-huh.
Of the singularity. So, how these two are related?
Oh, like the Fukaya category being essentially symplectic, and then this Frobenius manifold seemingly talking about complex things.
Seems so, but
Yeah.
yeah.
So I think, I think anything I say, I'm worried that it will be wrong. So maybe, I think maybe the idea is that it sort of doesn't matter what the symplectic structure is on the Fukaya side for the singularities I'm considering. But I think that that's probably wrong. So I have to say I don't know. I don't know why it's essentially complex when we talk about the Furbinius manifold, and yet this Fukaya category story is essentially symplectic. Yeah. But I mean, it's sort of like, so if you think about maybe the quantum cohomology case, you sort of need this symplectic form to talk about quantum cohomology, right? But the Frobenius structure there is also sort of a complex story. So yeah, I don't know. I don't know if there's something deeper here, or if this is just sort of how the setup is. Yeah. No, these Frobenius manifolds, I can't claim to even be a little bit of an expert on. I find them very complicated. So there's a lot of moving pieces, so maybe hidden somewhere is an answer to your question, but I am not the person to talk to, I suppose. Yeah.
Thank you. So there is a question in the chat from Chris. So beside the consecutive alpha and the Allojan Hotling papers, what are good references for this material?
Yeah.
References?
Yes. So some great references. I don't know which side of the board I should write this on. Maybe this side.
Yeah.
So some great references for this material. The main one that I used for at least the Frobenius manifold stuff is this book by Hertling which is something like Furbinius manifolds and moduli spaces of singularities. Let me just make sure that that is, I think I have the book here. Yeah. So, yeah, this is the right title. And then there's also this book, this great book by Sabah, which is Frobenius manifolds and isomonodromic deformations. Yeah. So as far as the Frobenius manifold story, I think that these two books are essential. As far as specifically this idea about the spectrum of an upper triangular matrix, I don't know if I've seen it anywhere except those two papers, the physics paper and this Balmajan and Hertling paper. So I don't know if there's other references. I mean, if you found other references for that, then I ask you to send them to me too. But as far as this whole Frobenius manifold story, these are fantastic books.
Okay, great. So is there any other question? Okay, now